For decades, we have comforted ourselves with the illusion of immeasurable reality, because we memorized that the age of the universe is 13.8 billion years, and so it seemed perfectly logical to assume that the absolute edge of everything we could see was exactly 13.8 billion light-years away in any direction. This math was clean, it was intuitive, and it felt safe. But it was also completely wrong, because the James Webb Space Telescope didn't just look deeper into the darkness, it tore up every single map we had. And so, let's begin by destroying a number you've accepted as absolute truth. The actual diameter of the observable universe is not 27.6 billion light-years. It is a mind-bending 93 billion light-years. This might come as a shock. Yay, because to understand how a 13.8 billion-year-old cosmos expanded to a domain almost 7 times wider than the distance light could travel in that time, you need to completely discard the idea that space is just an empty box that galaxies float in. Space is not empty. Space is a fabric that is actively stretching. To understand this, imagine trying to run towards someone on a moving walkway. But the walkway is constantly stretching out from under your feet, pulling you backward. When a distant galaxy emitted its light 13.5 billion years ago, it was actually much closer to us. But as that light began its agonizingly slow journey toward Earth, the cosmic treadmill started running, because the space between us and that galaxy was constantly expanding, carrying the physical galaxy outward, while its ancient photons fought to make their way across the growing void. That is why, when that light strikes the golden mirrors of the James Webb Space Telescope today, the galaxy that emitted it is no longer 13.5 billion light-years away. It has been dragged out to a distance of roughly 46.5 billion light-years in a single direction. When you look into the deep sky, you are actually looking at ghosts, because you're observing the fossilized afterimages of objects that have long since been swept toward the edge of an ever-expanding abyss. But that wasn't the real deception. The real deception was our belief about what was inside that 93 billion light-year sphere. For years, we stared into that emptiness, and we believed we understood its basic rules. Because when we looked deep into the cosmic past with earlier instruments like the Hubble Space Telescope, we saw a universe that grew increasingly sparse. The darkness felt utterly empty to us. But that emptiness was a lie, born from our own biological and technological limitations. As space expands, it also stretches the light that travels through it. It transforms the short, energetic wavelengths of visible light into long, slow infrared waves. So, by the time light from the deepest edges of the 93 billion light-year universe reaches us, it becomes completely invisible to the human eye and to telescopes built to see like us. The universe wasn't empty. It was just broadcasting on a frequency we couldn't tune into, and the James Webb Space Telescope was designed to capture precisely this invisible, redshifted frequency. It was built with a 6.5-meter beryllium mirror, coated in microscopic gold, to catch these ancient, tired photons, and it was parked 1.5 million kilometers from Earth. The expectation was that Webb would finally illuminate the quiet, fragile dawn of our 93 billion light-year bubble. But the telescope sent an unprecedented shockwave through the foundations of cosmology. It didn't just look deeper into the darkness, it proved that everything we thought we knew about this vast expanse was fundamentally and profoundly wrong. The terrifying truth of this scale is not just the sheer size of the volume of space we know, because we have known for a century that the universe is vast. The real horror is what Webb found inside it. The 93 billion light-year universe is neither empty, nor is it a patient, slow-moving machine. On the contrary, it is filled with massive galaxies that had already formed when the cosmos was just 300 million years old, because it was filled with monster structures and supermassive black holes that defied the rigid laws of physics we assumed for that era. When Webb captured hundreds of thousands of distinct, fully formed galaxies in patches of sky previously thought to be desolate voids, It proved that our understanding of this 93 billion light-year arena was essentially broken. We had built a map of reality based on mathematical models. But Webb's first deep stares into the infrared darkness confirmed our map did not match the terrain. Therefore, the true terror of this scale is our absolute ignorance of what is actually happening within it. But the 93 billion light-year lie runs even deeper than our misunderstanding of what it contains. This mind-boggling expanse, this field stretching 46.5 billion light-years in every direction, is not the entire universe. It is only the observable universe. It is a local bubble, defined entirely by the speed of light and the passage of time. The edge of this sphere is not a physical wall, or the end of space. It is an information event horizon, a one-way membrane beyond which reality continues in a way we can never permanently reach. By analysing cosmological data and applying advanced statistical modelling, physicists have calculated that the true universe extends far, far beyond this boundary. Conservative estimates suggest the total universe is at least 250 times larger than the observable portion we can map. Think about that. If the entirety of everything humanity has ever seen, measured, or theorised, this entire 93 billion light-year expanse were a single page in a book, the real universe would require a book of at least 250 pages. Everything the James Webb Space Telescope has dismantled, the impossibly large early galaxies, the rule-breaking black holes, the fundamental violations of cosmic architecture, is all happening in less than 1/250th of the true universe. And so, to truly understand the horror that James Webb has revealed, we must first go back to the absolute beginning and immerse ourselves in the darkest period of cosmic history. We must immerse ourselves. Imagine a universe where light was completely absent. Because, as the unimaginable initial heat and violence of the Big Bang began to subside, the cosmos expanded, and as it expanded, it cooled. About 380,000 years after the initial spark of creation, the universe had cooled enough for protons and electrons to finally combine and form the first neutral hydrogen atoms. When this happened, the primordial fog of free-floating electrons that had trapped all radiation finally cleared. But, after that brilliant flash, the lights went out completely. The universe entered a period cosmologists know as the Cosmic Dark Ages. For hundreds of millions of years, there were no galaxies, no stars, no planets, and absolutely no light. There was only a vast expanding void filled with a cold, invisible ocean of neutral hydrogen gas and the silent, unseen scaffolding of dark matter. This was a universe of utterly impenetrable darkness. And so, the emergence from this suffocating darkness is a period scientists call the Epoch of Reionization. This is the theoretical age when the first primordial stars and galaxies finally ignited, releasing a torrent of fierce ultraviolet radiation that began to burn through the fog of neutral hydrogen, slowly making the universe transparent. Understanding exactly how and when this happened wasn't just a secondary goal for astronomers. It was the primary mission of the James Webb Space Telescope. Humanity spent tens of billions of dollars to build an instrument with a 6.5-meter golden mirror, and parked it 1.5 million kilometers from Earth in the freezing void of space, for the express purpose of looking back 13 billion years and witnessing the exact moment the cosmos turned on the lights. But, before Webb opened its golden eye, the scientific community had a deeply ingrained, mathematically elegant expectation of what that cosmic dawn would look like. Because that expectation was defined by the standard model of cosmology known as lambda cold dark matter. This framework had been developed through over 40 years of painstaking observation and supercomputer simulations, and it had passed nearly every test astronomers had thrown at it. This model offered a comforting, just logical, and highly structured narrative for how existence assembled itself from the void. According to the lambda cold dark matter model, the universe is governed by the patient, methodical power of gravity, and so, the rules of the model dictate a process known as hierarchical merging. In simple terms, this means the small things must form first. Larger structures can only be built gradually, over immense periods of time, by combining those smaller pieces. In the deep darkness of the early universe, regions of dark matter that were slightly denser than average exerted a weak gravitational pull. Over tens of millions of years, they slowly gathered more dark matter, and they grew into vast, invisible gravitational wells called halos. Only then could ordinary hydrogen gas begin to be patiently drawn into these unseen valleys. Because the gas needed to slowly cool, lose its energy, and fragment. Only then could it collapse under its own weight to ignite the very first stars. This is an extremely slow, inefficient yet an agonizingly gradual process. Gravity is powerful, but it takes time. You cannot build a skyscraper without pouring the concrete, and you cannot pour the concrete without surveying the land. Because of these rigid physical speed limits, every cosmological model predicted that the universe's first galaxies would be incredibly small, incredibly faint, and incredibly rare. They were expected to be fragile, primitive smudges of starlight, barely clinging to existence. And it was thought it would take hundreds of millions of years for them to evolve into anything resembling the massive, structured galaxies we see in the local universe today. And so, when astronomers pointed the James Webb Space Telescope at the deepest, oldest corners of the night sky, they were fully prepared for a landscape of scarcity. They expected to find a cosmos that was quiet, hesitant, taking its first tentative steps out of the darkness. But what they found instead shattered 40 years of established theoretical physics. As the telescope's advanced deep extragalactic survey, thus known as JWST, began to meticulously analyze the faint infrared photons from the edge of the observable universe, the data did not reveal a silent, empty dawn. On the contrary, it revealed a cosmos that was already crowded. It showed a universe blazing with light. It was filled with massive, structured galaxies producing a shocking amount of starlight. The universe wasn't slowly waking up. It was already running at a terrifying, fiery pace. The absolute collapse of our expected timeline was crystallized by the discovery of a single impossible object. Because, deep in the survey data, astronomers spotted a galaxy with the cold, bureaucratic name of JWST-GS-Z 14-0. At first, it appeared as just another faint reddish smudge. But when researchers pointed the telescope's near-infrared spectrograph at this object, everything changed. Because when they split its ancient light into its component wavelengths and read its cosmic fingerprint, the resulting data sent a shockwave through the astronomy community. The spectrograph measured a redshift of 14.32. This number was not an ordinary measurement. In the physics of an expanding universe, just your redshift is the ultimate measure of both distance and time. Because, as light travels across billions of light years, the very fabric of space stretches beneath it, pulling the light waves to longer, redder frequencies, and so a redshift of 14.32 signifies a specific, undeniable moment in the history of reality. It means the light captured by the telescope left this galaxy when the universe was exactly 290 million years old. To grasp why this number is so mathematically terrifying, you must set aside the vastness of human history and think on the brutal scale of cosmic time. Because our universe is roughly 13.8 billion years old, 290 million years is therefore a mere fraction of that timeline. It represents exactly 2% of the universe's current age. If you were to compress the entire 13.8 billion year lifespan of the cosmos into a single 12-month calendar year, the Big Bang happens in the first second of January 1st. The galaxy JWST-GS-Z 14-0 was fully formed and burning violently in the first week of January. To understand this speed, let's compare it to a timeline you know, the ground beneath your feet. The Earth has existed for about 4.5 billion years. The dinosaurs ruled our planet for roughly 165 million years before they were annihilated. But now look back to the young universe. In less than twice the time it took for a single species of reptile to evolve, thrive, and be extinguished on one small rock, the entire universe emerged from a formless quantum fireball. It built the invisible scaffolding of dark matter. It collected unimaginable oceans of primordial gas. It ignited millions of thermonuclear star engines. and it organized them into a massive functioning galactic metropolis. This speed defies every logical limit set by the lambda cold dark matter model, because a galaxy at 290 million years after the Big Bang should have been nothing more than a barely detectable flicker. But JWST-GS-Z14-0 was not a flicker. It was an absolute monster. The data revealed this galaxy was more than 1,600 light-years across. It was incredibly bright, and the source of this blinding luminosity was not the play of an actively feeding black hole. It was the combined plus ferocious output of hundreds of millions of young gas massive stars. Think about the mechanical requirements of what you just heard. The standard model dictates that typical galaxies convert only a small fraction of their available gas into stars. But for this galaxy to have assembled hundreds of millions of solar masses worth of stars in just 290 million years, it would have had to convert nearly 100% of every available atom of gas into stars at an impossibly sustainable rate. This level of star formation efficiency is not just improbable under our current understanding of astrophysics, it is essentially forbidden by the laws of thermodynamics. Yet, the terrifying reality of JADES-GS-Z14-0 extends far beyond its mass and luminosity. Because the real horror is hidden in the chemical signature of its ancient light. When astronomers analysed the spectrum of this impossibly early galaxy, they expected to find nothing but hydrogen and helium. The Big Bang was a tremendous furnace of heat, but it was incredibly brief. It only had the capacity to forge the very lightest elements in existence: the carbon in your DNA, the iron in your blood, the silicon in the earth, and the oxygen you breathe. Every single heavy element in the universe did not exist at the dawn of time. They are byproducts of cosmic violence. Because they can only be forged in the crushing, multi-million degree cores of massive stars. But according to the models that existed before this telescope was launched, the first primordial stars weren't even expected to begin igniting until the universe was 100 to 200 million years old. This finding was, as one of the lead researchers stated plainly, completely unexpected. And now comes the real shock. Because this is not just a small anomaly, it was the harbinger of a massive, systemic failure in our understanding of reality. And JADES-GS-Z14-0 was not alone. As the telescope continued its deep surveys, it began to catalogue an entire population of these objects, galaxies appearing at redshifts above 10 that completely defied the limits of how quickly matter could organise itself. Researchers examining data from the Cosmic Evolution Early Release Science Survey (CEERS) identified a half-dozen galaxies that formed within the first 500 to 700 million years and contain up to 100 billion times the mass of our Sun. This means the infant universe was somehow building galaxies with stellar masses similar to the modern-day Milky Way, but it was doing so in less than 5% of the time it took the Milky Way to assemble itself. These objects defied the model so violently and so consistently that the stunned researchers who found them gave them a new, unofficial classification. They called them universe breakers, and the name was terrifyingly accurate. If the lambda cold dark matter model is correct, these galaxies cannot exist. Gravity is too weak, gas cooling is too slow, and the universe was simply too young. The standard model demands a slow, hierarchical merger, a patient gathering of dark matter and gas over billions of years. But the James Webb Space Telescope proved the universe didn't wake up slowly. It ran. It transcended the patient rules of hierarchical merging, and it somehow forced massive, chemically enriched structures into existence in an impossibly compressed time frame. The early cosmos was not a delicate, quiet dawn. It was a savage, hyper-efficient age of violence. It was a universe running at a rate and intensity that no longer exists. The terrifying mystery we face is not just how these universe breakers formed, but what unknown, unrecognized physical laws allowed them to do so. If our fundamental model for how gas collapses, how stars ignite, and how galaxies merge is completely invalidated by the very first things that existed, then we are completely blind to the true mechanisms of creation. We have spent our entire scientific history studying the slow, aging embers of the modern universe, because we falsely believed we understood the fire that started it. But Webb has forced us to look directly into that ancient fire, and what it showed is a mechanism of creation so hyper-powered, so incomprehensibly fast, that we are now forced to consider the deeply unsettling possibility that we do not actually understand how our own universe was built. To fully grasp the horror of the anomalies lurking in the early cosmos, we must first look closer to home and understand the delicate, seemingly permanent balance that governs our own galactic neighborhood. Because, sleeping deep in the core of the Milky Way galaxy lies a slumbering giant, a supermassive black hole known as Sagittarius, a star weighing in at about 4 million times the mass of our Sun. While 4 million solar masses sounds like a terrifying concentration of gravity, it is actually quite small in the grand architecture of our galaxy. The Milky Way has roughly 60 billion solar masses worth of stars. But when you do the math, you find that the mass of our central black hole represents only 1/10 of 1,000th of a percent of the total stellar mass of the entire galaxy. In the modern-day universe, this relationship is not a coincidence. It is a rigid, universally observed rule. Because, over billions of years of cosmic time, black holes and their host galaxies appear to be locked in a patient, harmonious dance. The models that dictated cosmic evolution assumed they grew together. In tandem, a galaxy gathers gas, it forms stars, and slowly, over billions of years, a small fraction of that material trickles to the center, feeding the black hole. It maintains a proportional, balanced ratio, where the galaxy is always vastly more massive than its central engine. But, when the James Webb Space Telescope pointed its golden mirrors into the deepest infrared abyss, it proved this harmonious balance is a modern illusion. The baby universe was not a place of balance. It was a place of extreme, terrifying disproportions. It was ruled by monsters that were far too large for their cages. Hidden within the deep survey data, astronomers began cataloguing a strange new class of object, one with no clean precedent in the local universe. Because, as their ancient light was stretched by billions of years of cosmic expansion, they appeared as compact, intensely red specks against the darkness of space. This earned them the informal, almost innocuous-sounding name of little red dots. But, as teams led by researchers like Jorrit Matthey from the Austria Institute of Science and Technology began to extract the spectral fingerprints from 341 of these catalogued objects, the data shattered the illusion of a quiet cosmic dawn. These little red dots, existing roughly 600 million to 1.3 billion years after the Big Bang, were 10 to 100 times more abundant than any cosmological model had predicted, but their sheer numbers were nothing compared to the nightmare hiding at their centers. Because the supermassive black holes anchoring these ancient systems range from 1 million to 100 million solar masses. When the astronomers compared the mass of these black holes to the stellar mass of the tiny, compact galaxies that surrounded them, the equations broke. The 1,000th% rule was utterly destroyed. Because, in the little red dots, the central black hole accounted for 30% or more of the entire mass of its host galaxy. That is a factor 300 times larger than the locally observed relationship. In some of these systems, the black hole actively outweighs the combined mass of every single star in the galaxy. The relationship is completely inverted. Imagine the Milky Way. But, instead of a quiet core, it hosts a gravitational monster 300 times larger, violently dwarfing all the galactic structure around it. These are not galaxies that contain a black hole. They are massive, insatiable black holes, barely disguised as a galaxy. And so, this inverted ratio has thrown astrophysics into a serious crisis. The models dictated that a galaxy must form first, patiently building its stellar mass, while the black hole slowly feeds on the leftovers. But the little red dots show that in the early universe, the black hole got huge first, savagely outgrowing its surrounding galaxy, dominating the system's mass budget, leaving the stars as a tiny afterthought. So how is this even possible? To understand why this disproportionate growth is not just surprising, but physically alarming, you need to understand that the universe has a rigid mathematical speed limit for growing a black hole. Because this limit requires overcoming a fundamental barrier of physics, and this barrier requires overcoming. So what exactly is the mechanism behind this? Growing a supermassive monster weighing millions of solar masses from a small stellar seed is not simply a matter of dumping matter into a bottomless pit. Because the process takes time, and it demands overcoming a fundamental barrier of physics. So let's get technical now, and see what laws the universe was breaking to build these impossible monsters. As massive clouds of gas and dust fall toward a black hole's event horizon, the material cannot simply plunge straight in. Because it spirals around the center, forming a dense, flattened ring known as an accretion disk. As this material packs together and moves at significant fractions of the speed of light, immense friction heats the gas to millions of degrees. The disk therefore becomes a blazing inferno, radiating blinding amounts of radiation, particularly high-energy X-rays. But light has momentum. It exerts a physical force. As the black hole feeds aggressively, the intense radiation blasting out from the superheated accretion disk pushes back against the incoming gas. Gravity pulls the food in, but light pushes the food out. If too much matter falls toward the black hole too quickly, the outward radiation pressure becomes so powerful that it literally blows the black hole's own fuel supply away into deep space. The black hole effectively chokes on its own light, and this prevents it from feeding any faster. And so, this delicate balance between gravity pulling in and radiation pushing out creates a hard theoretical ceiling on how quickly a black hole can physically grow. In astrophysics, this maximum threshold is known as the Eddington limit. Because of this rigid speed limit, even if a black hole were constantly feeding at the absolute maximum allowed rate, building a supermassive black hole from a stellar remnant should require hundreds of millions or even billions of years of patient to steady accretion. Because the physics of infalling matter impose this rigid speed limit, and it functions as an unbreakable law of thermodynamics. But the James Webb Space Telescope has revealed that the early universe was a chaotic, lawless frontier that simply ignored the rules. The most terrifying evidence of this cosmic rebellion comes in the form of an object with the bureaucratic name of UHZ1. Sitting at the center of a dwarf galaxy, UHZ1 is a black hole observed as it existed approximately 470 million years after the Big Bang. When the combined observations of the James Webb Space Telescope and the Chandra X-ray Observatory analyzed the high-energy light radiating from this system, the data came back with a number that defied reality. UHZ1 wasn't just eating efficiently, it was consuming matter at a rate more than 40 times the theoretical Eddington limit. 40 times. This is not a small anomaly or a slight miscalculation, it is an act of extreme physical violation. To put the absurdity of this measurement in perspective, if the Eddington limit were a highway speed limit of 100 km per hour, UHZ1 is screaming down the road at 4,000 km per hour. The physics of radiation pressure dictates this is utterly impossible. The outward force of the X-rays screaming from the accretion disk should have long since blown its gas supply into intergalactic space. Yet, UHZ1 is gorging itself in a blaze of blinding light, completely ignoring the fundamental speed limits of reality. And so, faced with monsters larger than their cages and entities that transcend universal speed limits, theoretical physicists have been forced to propose terrifying mechanisms that define an impossibly violent early cosmos. To explain UHZ1, scientists have turned to a phenomenon called super-Eddington accretion. For this to happen, matter can't just be gently spiraling into the black hole. It has to be pouring into the event horizon from all directions at once, in such an overwhelming, suffocating volume that the radiation pressure is simply overwhelmed. Imagine standing in front of an oscillating fan and trying to stop a roaring Kolkiaskia ocean-sized tidal wave. The wave wins by sheer overwhelming mass. If massive amounts of dense turbulent gas collapse onto the black hole all at once, the radiation cannot push it away fast enough, leading to a brief violent feeding frenzy. JWST suggests that in the crowded, chaotic environment of the early universe, these extreme rule-breaking feeding events were not rare coincidences, but a common feature of cosmic architecture. But even super-Eddington accretion struggles to fully explain the sheer abundance of the little red dots. or how their central engines got such a massive head start on their host galaxies. Which brings us to a second, even more disturbing theory. What if the early universe was skipping the traditional life cycle of stars entirely? In the standard model, a black hole must begin as the remnant core of a dead star, perhaps weighing 50 times the mass of our Sun, and this core must begin the agonizingly slow process of feeding. But the early universe may have had a terrifying shortcut. Cosmologists have proposed the concept of direct collapse black holes. In the high-pressure, radiation-soaked environment of the young cosmos, a massive cloud of primordial hydrogen gas, weighing tens or even hundreds of thousands of solar masses, could simply collapse in on itself under its own immense gravity. Because this primordial gas lacked the heavy elements that normally allow clouds to cool and fragment into smaller stars, the entire massive cloud collapsed directly into a singularity. This direct collapse would have formed a heavyweight seed from birth, skipping the star phase entirely. Instead of starting from a 50 solar mass remnant, the black hole would begin its life already weighing 100,000 times the mass of our Sun, giving it a massive, unfair advantage in the race to accumulate mass. A closely related theory suggests the existence of supermassive stars, theoretical giants hundreds or thousands of times larger than typical stars. After burning ferociously for a few short million years, these stars would have exploded and collapsed into equally massive black hole seeds. Both the direct collapse and supermassive star theories require highly specific, just extreme conditions that simply do not exist in the modern universe, and this paints a picture of an ancient cosmos operating under a very different, much more volatile set of rules. What the little red dots and the insatiable appetite of UHZ-1 ultimately reveal is a massive structural failure in our understanding of how reality is put together. But what if these structures were not just big, but also chemically impossible? Because of the next layer of what Webb has revealed contains an anomaly that threatens not just the laws of gravity, but time itself, forbidden chemistry. It holds. And so, to truly understand the depth of the deception we are trapped in, we must look beyond the sheer size of the early galaxies the telescope discovered and examine the very atoms they are made of. Because, if the impossible masses and insatiable black holes of the baby cosmos challenge our understanding of gravity, the chemical signatures hidden in their ancient light threaten to completely annihilate our understanding of time. There is a fundamental law of reality. It governs the physical world you interact with every single day. Because the carbon that structures your DNA, the oxygen that fills your lungs, the iron that carries blood through your veins, and the silicon beneath your feet all share a single, violent origin story. None of these elements existed at the dawn of time. When you set aside the complexity of the modern cosmos and rewind the clock to the absolute beginning, the universe was incredibly, brutally simple. But the Big Bang, while an event of unimaginable heat and energy, was also incredibly brief. The extreme temperatures needed to forge atomic nuclei lasted only for a few minutes, and so, in that brief window of time, the universe functioned as a primordial furnace, but it only had the capacity to forge the simplest, lightest elements in existence. As the cosmos expanded and cooled, it was locked into a permanent base inventory of matter, vast oceans of hydrogen, a smaller percentage of helium, and an incredibly faint, almost negligible trace of lithium. That was it. Because, for the first few 100 million years of existence, the periodic table of elements stopped there. Because of this rigid limitation, every single heavy element in the universe is a byproduct of cosmic violence. They cannot simply appear in the vacuum of space. To forge carbon, oxygen, nitrogen, and iron, the universe needs high-pressure, specialized factories, and those factories are stars. A star is not just a beacon of light. It is a multi-million-year-long sustained thermonuclear explosion held in a delicate state of equilibrium by the crushing weight of its own gravity. Deep in the multi-million-degree core of a star, immense pressure violently smashes hydrogen atoms together, forcing them to fuse into helium, releasing the energy that makes the star shine. But when a star exhausts its supply of hydrogen in its core, it begins a desperate, agonizing sequence of collapse and reignition, fusing heavier and heavier elements simply to escape the crushing weight of its own mass. Helium fuses into carbon, carbon into oxygen, oxygen into neon, and eventually, in the most massive stars, the core fuses into iron. But forging these heavy elements is only the first half of the requirement. Because an element trapped in the dead core of a star is useless to the rest of the universe, to seed the cosmos with the building blocks of planets, chemistry, and ultimately life, that star must die a catastrophic death. When a giant star finally runs out of nuclear fuel, gravity wins the billion-year-long battle in a fraction of a second. The star's core collapses inward at a significant fraction of the speed of light. It hits a limit of absolute density, and it rebounds in a shockwave of unimaginable power. The star explodes as a supernova. And so, only through this final act of sacrifice are the heavy elements forged deep in the stellar core violently distributed into the surrounding interstellar space. Once ejected, these enriched clouds of gas slowly cool, mix with primordial hydrogen, and eventually collapse again to form the next generation of stars. This new generation incorporates the heavy elements from the ashes of the old, allowing for the formation of rocky planets and the complex chemistry required for life. The atoms that make up your body were literally forged in the cores of stars that lived, burned, and exploded billions of years before our solar system ever existed. Because of this unbreakable chain of physical processes, chemistry functions as a cosmic clock. Because yes, the presence of heavy elements in a galaxy is absolute, undeniable proof that an entire generation of stars has already lived its full life and died. In astronomy, any element heavier than helium is generically referred to as a metal, and tracking a galaxy's metallicity is how scientists read its age. You cannot skip the clock. A galaxy cannot fake its chemistry. If you detect heavy elements, you are looking at a system that has already been subjected to immense spans of time, multiple stellar life cycles, and widespread supernova activity. When astronomers point their telescopes at the local, modern-day universe, they see galaxies rich with these heavy metals, the result of 13.8 billion years of continuous cosmic recycling. But when they used the James Webb Space Telescope to look at the deepest, oldest edges of the observable universe, the expectation was completely different. They were aiming their spectrographs at galaxies that existed only a few 100 million years after the Big Bang. At this extreme distance, looking at the dawn of structure formation, the models dictated they should find absolutely pristine, unpolluted environments. But when the combined observations of the James Webb Space Telescope and the Atacama Large Millimeter/Submillimeter Array analyzed the impossibly large, impossibly early galaxy known as JADES-GS-C 14-0, they detected a blatant, unmistakable spectral emission line. They found oxygen. They detected oxygen sitting in a fully assembled galaxy that existed when the universe was only 290 million years old. To grasp the paralyzing fear this single chemical signature sent through the astrophysics community, you must understand the unbearable compression of time it demands. Because, in the timeline dictated by the standard model of cosmology, the 290 million-year-old universe was supposed to have barely emerged from the cosmic dark ages. The first primordial stars weren't even expected to begin igniting until the universe was 100 to 200 million years old. But if the first stars are just beginning to burn at the 200 million year mark, how can a massive, brightly burning galaxy, saturated with oxygen, exist at the 290 million year mark? Because, for oxygen to be radiating from a galaxy at this age, the universe could not have wasted any time. The entire agonizingly slow chain of cosmic creation would have to have been radically, violently compressed into a span of time that is mathematically just a rounding error in the life of our own Milky Way. The baby universe would have had to collect primordial gas, ignite a first generation of stars, allow those stars to live their entire lifespans, wait for them to explode in catastrophic supernovae, allow the ejected oxygen to mix with surrounding gas clouds, and then channel the enriched gas into a second generation of stars large enough to form a galaxy 1,600 light-years across. The timeline of reality is uncomfortably, terrifyingly compressed. This is like excavating an ancient Roman ruin and finding a fully functional smartphone among the stones. The universe's technology was far too advanced for the era in which it was found. In the face of this impossible chemistry, scientists are being forced to invent monsters to make the math work. If the universe managed to forge oxygen this early, it means the very first stars that existed could not have been normal. They would have had to have been leviathans. Theorists call them population 3 stars, but the term fails to capture their terrifying nature. Because just formed from the pure, unpolluted hydrogen and helium of the Big Bang, without any heavy elements to help the collapsing gas clouds cool, they could not fragment into normal-sized stellar masses. Instead, the gas collapsed into monolithic and supermassive structures. These population 3 monster stars are theorized to have weighed between 1,000 and 10,000 times the mass of our Sun. They would have been the largest, most violent, and most intensely burning objects that have ever existed. Because of their unimaginable mass, their cores would have been pressurized to degrees we can barely model, forcing them to fuse elements at a furious, runaway pace. While a star like the Sun will burn peacefully for 10 billion years, these primordial monsters would have consumed their entire fuel supply in a blinding flash of cosmic time, living for perhaps only a few million years before they collapsed, and their deaths would have been equally absolute. They would not just have exploded, they would have gone hypernova, the most energetic explosions possible under the laws of physics, tearing themselves apart so violently that they would have sprayed millions of Earth masses of newly forged oxygen, carbon, and nitrogen into the depths of the primordial darkness. And so, the detection of oxygen at 290 million years requires that entire generations of theoretical monsters must have lived, burned, and annihilated themselves with terrifying intensity before the universe was even 3% of its current age. The cosmos did not wake up slowly. It exploded into existence with a ferocity that threatens to break our understanding of how matter behaves. But here is the truly exciting part. If our fundamental model is invalid, it affects not only the past, but the future. And this brings us to the collapse of the cosmic web. The fact that even the largest structures in the universe are impossible. They are. And now, to truly understand the depth of the deception we are trapped in, we must shift our gaze away from the microscopic chemistry of ancient stars and the impossible feeding rates of singular black holes. We must stop looking at the isolated puzzle pieces, and we must step back to examine the architecture of the game board itself. Because this will take us to the pinnacle of the entire universe, its most epic discovery, and its most incredible truth. We are accelerating. Get ready. When you stand outside on a clear night and look up at the sky, human intuition tells you that the universe is just an infinitely large, empty container where stars and galaxies are randomly distributed like dust thrown against a black backdrop. But as the James Webb Space Telescope and its companion observatories map the deepest reaches of the cosmos, they have confirmed this intuition is a complete illusion. Galaxies are not randomly distributed in space. They do not drift aimlessly in the dark. They cluster, they align, and they follow invisible, highly specific pathways across enormous distances. When you zoom out far enough, the universe ceases to look like a loose collection of isolated objects, and it begins to resemble a vast, interconnected biological nervous system. This is the cosmic web. It is the largest coherent structure in existence. It spans the entire 93 billion light-year diameter of the observable universe, and it organizes everything we can see into a staggering 3-dimensional foam. The architecture of this web is dictated not by the glowing visible matter, but by the dark matter we cannot see. Because, outnumbering normal matter 5-to-1, dark matter provides an invisible scaffolding for reality itself. Shortly after the Big Bang, tiny quantum fluctuations in the density of the universe were magnified by gravity over hundreds of millions of years. Dark matter was the first to respond to these fluctuations. It gathered in quietly growing concentrations, and it formed vast invisible filaments. These filaments of dark matter stretch for tens to hundreds of millions of light years across the void, and they function as the structural girders of the cosmos. Ordinary matter, the hydrogen and helium gas that would eventually become stars, planets, and people, simply followed this invisible blueprint. Because, gas was drawn into the dark matter valleys, it cooled, and it condensed into galaxies in the places the dark matter dictated. Today, galaxies flow along these cosmic highways, pulled by gravity like rivers of starlight, constantly draining into massive cosmic ocean basins. Where multiple filaments intersect, matter accumulates in unimaginable quantities, and it forms the bright but dense nodes of the web. These nodes are galaxy clusters. They are the largest gravitationally bound objects in the universe, where hundreds or thousands of galaxies violently interact in a space only a few million light-years across. But an architecture built on dense, interconnected threads requires the existence of something equally terrifying: the spaces left behind. Because between the glowing filaments and crowded intersections of the cosmic web lie the voids. These are vast regions of space, spanning tens to hundreds of millions of light-years in diameter, where structure formation simply did not happen. As gravity spent billions of years pulling matter toward the dense filaments, these regions were progressively emptied, leaving behind an almost perfect vacuum. If you were to place the Earth at the center of a typical cosmic void, the surrounding emptiness would be so absolute that our astronomers would not have even known other galaxies existed until the invention of deep space telescopes in the 1960s. This extreme, terrifying contrast, a universe of hyperdense, chaotic filaments separated by oceans of unimaginable, desolate nothingness, poses a massive problem for physicists trying to calculate the fundamental laws of reality. Because, in order to mathematically describe the universe, to calculate its precise age, to measure its exact expansion rate, and to map its total size, scientists require the universe to be predictable. The entire field of modern cosmology is built on a single, foundational assumption, an assumption introduced by Albert Einstein himself when he applied his equations of general relativity to the universe as a whole, known as the cosmological principle. The cosmological principle is a declaration of cosmic order. It states that on large enough scales, the universe must be both homogeneous and isotropic. In simple terms, it assumes that when you zoom out far enough, past the individual galaxies, the dense clusters and the vast voids, the universe must eventually average out. It must resolve into a smooth, uniform, featureless expanse. But this principle carries a very specific mathematical requirement for the maximum allowed size of any structure in the cosmos. Based on the laws of physics and the time available since the Big Bang, standard models dictate that no coherent structure in the universe should be larger than approximately 1.2 billion light-years. Above that scale, gravity simply has not had enough time to organize matter, and the universe must dissolve into statistical uniformity. For decades, the math held. But, as our survey instruments grew more powerful, disturbing cracks began to appear. In 2003, astronomers discovered the Sloan Great Wall, a massive filamentary structure that stretched for about 1.37 billion light-years. It sat just over the theoretical limit. But then astronomers started looking for the most violent explosions, gamma-ray bursts, as a way to map the underlying architecture of the cosmic web at the most extreme scales. In 2013, a research team led by Istvan Horvath analyzed the distribution of these violent beacons in the sky, and they found a clustering of gamma-ray bursts that defied all mathematical logic. There was a concentration of mass so large and so dense that it completely broke the equations of cosmic evolution. But in April of 2025, an expanded, rigorous analysis using a much larger catalogue of bursts confirmed the detection with devastating statistical significance. They had not found a coincidence, they had found a monster. And now comes the real shock. They named it the Hercules Corona Borealis Great Wall, after the constellations of its enormous footprint in our night sky. It is a single coherent wall of galaxies, gas and dark matter, and it stretches for a mind-boggling 10 billion light-years in length and roughly 7.2 billion light-years in width across space. To grasp the horror of this measurement, you must compare it to the absolute limits of reality we have already discussed. The entire observable universe, the absolute maximum boundary of what humanity can ever see, is 93 billion light-years across. The Hercules Corona Borealis Great Wall is 10 billion light-years long. This means this single continuous structure takes up more than 10% of the diameter of the entire observable cosmos. Under the rigid laws of modern physics, this structure is completely impossible. The theoretical speed limit for the largest allowed coherent structure is 1.2 billion light-years. The Hercules Corona Borealis Great Wall is more than 8 times larger than it is legally allowed to be. Gravity has not had enough time since the Big Bang to communicate across a distance of 10 billion light-years, let alone organize that much matter into a single coherent filamentary wall. There is absolutely no physical mechanism in the standard model of cosmology that can produce a structure of this size. But there it is, and its existence creates an apocalyptic crisis in the field of astrophysics. This is not a small anomaly that can be patched over with a new variable or a slight adjustment to the equations. Because its sheer size guarantees that the universe does not smooth out. The cosmological principle is dead. The foundational assumption of Albert Einstein, the bedrock upon which every single modern equation of cosmic evolution has been built, is fundamentally wrong. The universe is not homogeneous, it is not isotropic, and the rules are not applied equally everywhere. The horror of this realization is not just philosophical. It cascades down to every single measurement we have ever made about the reality we inhabit. If the universe is not uniform, then the math we use to define the scale of the universe is completely invalid. Because we use the cosmic microwave background to calculate a global expansion rate because we assume the universe is expanding equally in all directions. But if the cosmos is lopsided, choked with unbalanced, 10 billion light-year wide hyperdense walls of matter on one side and unimaginably large voids on the other, then gravity is pulling unevenly across the expanse, which means that comforting number we started with, the 93 billion light-year diameter of the observable universe, may be nothing more than a local illusion derived from a broken formula. The James Webb Space Telescope and its massive survey programs have confirmed that the largest structures of the cosmos are in open violation of the mathematical models we use to understand them. And so, the cosmological principle, the one thing that was supposed to be a way of imposing human logic and mathematical symmetry on an incomprehensible abyss, is no longer a security blanket. Now that blanket has been violently ripped away, exposing us to a cosmos that is far more unpredictable and hostile to our equations than we ever feared. But the horror of our broken perspective does not stop at the distant edges of the Hercules Corona Borealis Great Wall. Because if the geometry of the entire universe is warped by an uneven distribution, we must eventually look at our own feet. We must ask where exactly we are standing inside this chaotic, unbalanced web. And as we will discover in the next chapter, our specific address in the cosmos is not just ordinary. We are trapped inside a massive gravitational anomaly of our own, and we are observing reality from inside a funhouse mirror that may be systematically blinding us to the truth. But how is this mirror distorting everything we see? And the real question is, how does this distortion change everything we thought we knew about the end of the universe? Because the real apocalypse is hidden inside the mirror, it is. And so, every great revolution in astronomy has been based on a single, humbling demotion. The realization that there is absolutely nothing special about our position in the universe. We learned the Earth does not sit at the center of the solar system. Our Sun does not sit at the center of the galaxy. And the Milky Way is just one ordinary system among trillions. But the James Webb Space Telescope has forced us to confront a terrifying possibility. What if our window is fundamentally warped? What if the very fabric of space surrounding our solar system is a local anomaly that is actively distorting the light that reaches us? The answer to these questions lies in a crisis that is tearing apart our entire perception of the universe. The Hubble tension. This tension revolves around perhaps the most important number in all of cosmology, the Hubble Constant. This number represents the exact rate at which the universe is currently expanding. Knowing this precise rate is how we calculate the age of the cosmos, how we map the 93 billion light-year boundary of the observable universe, and how we predict the ultimate fate of reality. Because Determining this constant with absolute certainty has been the primary obsession of observational astronomy for 30 years. To find it, scientists use the two most powerful precision measurement methods humanity has ever devised. The problem is, those two methods are giving two completely different answers, and neither one of them can be mathematically wrong. The first method involves looking as far back as physics will allow, and measuring the expansion rate of the early universe. To do this, astronomers study the cosmic microwave background radiation, the faint, dim afterglow of the Big Bang itself. From these primordial patterns, measured by instruments like the Planck satellite, they can run the standard model of cosmic evolution forward like a computer simulation, and predict exactly how fast the universe should be expanding today. This incredibly precise, yet mathematically rigorous method gives an expansion rate of about 67 kilometers per second per megaparsec. But the second method ignores the ancient past, and it measures the expansion rate of the local universe directly. Astronomers build what is known as the cosmic distance ladder. They start by measuring the precise distances to nearby pulsating stars called Cepheid variables, and they extend that measurement out to violently exploding stars in distant galaxies called Type 1 a supernovae. When astronomers use this direct physical measurement of the local universe, the answer comes out to be about 73 kilometers per second per megaparsec, 67 versus 73. This, in the unforgiving, hyper-precise field of cosmology, is an apocalyptic failure. The gap between the two measurements is at a devastating 5 to 6 sigma level, which means there is a 1 in a million chance it is a random statistical coincidence. The discrepancy is not an error. It is an undeniable, blatant contradiction in the physical behavior of reality. For years, the scientific community clung to a desperate, comforting hope. They told themselves the models were not broken, the instruments were flawed, but in 2023, that hope was violently extinguished. Because, when Webb pointed its 6.5-meter golden mirrors at the same key, Cepheid variables and supernova used in previous measurements, it did not find an error. The new telescope confirmed the Hubble Space Telescope measurements with terrifying precision. The instruments are not flawed. The Hubble tension is absolutely real, so how is this possible? If the telescopes are working perfectly, and the math that governs the cosmic microwave background is sound, then we are left with a terrifying conclusion. The discrepancy is not coming from a mistake in how we are looking. The discrepancy is coming from where we are standing. We know the universe is not a homogeneous ocean of stars. It is a complex and unbalanced web, where hyperdense filaments of dark matter are separated by staggering oceans of emptiness known as voids. And we do not live in an average region. We are trapped inside a massive gravitational anomaly of our own. It appears we live inside a void. This structure is known as the KBC void, named after the three researchers, Keenan, Barger, and Cowie, who systematically characterized it. The KBC void is a vast, largely underdense region of space, where the average density of matter is significantly lower than the cosmic average. But the true horror of the KBC void is its unimaginable size. The boot is void, so incomprehensibly large it shamed its discoverers, spans 330 million light-years. The KBC void is 6 times larger. It is a spherical bubble of emptiness, a staggering 2 billion light-years in diameter. It encompasses not just the Milky Way, but our entire local group of galaxies, the massive Laniakea supercluster with its 100,000 galaxies, and the surrounding area for hundreds of millions of light-years in every direction. Our solar system is located somewhere within the interior of this anomaly. What is our place in this picture? For all of human history, we have believed the forces of nature are constant. But recent data has revealed a terrifying truth. The operating system of the universe is not stable, and this leaves us with 3 fundamental paradoxes, 3 brutal yet beautiful truths. The first paradox is that of scale itself. On one hand, you have the unimaginable vastness of the 93 billion light-year observable universe, an expanse that holds more than 2 trillion galaxies, each with hundreds of billions of stars. But, on the other hand, there is you, a being roughly 1.7 meters tall, living on the surface of one tiny planet with an average lifespan of 80 years. How can these two scales possibly come together? How can we bridge the gap between the vast architecture of the universe and your profoundly limited, fragile existence? The answer to this question contains a truth that is both tragic and beautiful. Because the tragic part is, you will never physically touch that vastness. Our fastest spacecraft would still have to travel for about 70,000 years to reach the nearest neighbouring star system, Proxima Centauri. That is longer than all of recorded human history, and that star is just one of 400 billion in the Milky Way. You cannot book a ticket to the edge of the 10 billion light-year Hercules Corona Borealis Great Wall. You cannot take a trip to the source of the ancient light of JADES-GS-Z 14-0. Your physical being occupies less than a single water molecule in this cosmic ocean. The vast majority of the cosmos will forever remain an unreachable dream for you, and this can create a feeling of profound cosmic loneliness. But this is where the word "but" comes in, and it changes everything. Because, while you cannot physically go there, your mind can. You're a piece of the universe, trying to understand the universe itself. You're a being made of the very same atoms that fill that 93 billion light-year expanse, and those atoms have somehow come together in a way that allows them to question, measure, and give meaning to that void. Yes, you're small, but you're also the only thing that can witness that unimaginable vastness, comprehend it, and stand in awe of its beauty. The James Webb Space Telescope is an extension of your curiosity. Those golden mirrors are a continuation of your eyes, and you, sitting in your home, can see the light of a star that exploded 13.5 billion years ago, analyze its chemical makeup, and ponder the meaning of its existence. This is not a weakness of being small, it is a power. Because as Skursund, you are like a mirror in which the universe looks at itself, and so, the size of the universe is not there to crush you, but to remind you of what an incredible thing you are a part of. The second paradox is that of time itself. On one hand, there is a 13.8 billion-year-old cosmos, an almost infinite amount of time for stars to be born, to die, and to be born again. A patient process for galaxies to collide and merge, billions of years for dark matter to slowly weave its web. But, on the other hand, there is you again, a lifespan that is a blink of an eye on the cosmic calendar. If the entire history of the universe were compressed into a single year, all of recorded human history would take place in the last 30 seconds. Your entire life would be just a momentary flicker. So, how can this transient existence find any meaning in that infinite ocean of time? The tragic truth is, you have missed most of the universe's grand story, and you will miss most of it to come. You did not see the first explosions of the population 3 monster stars. You did not witness the formation of the first galaxies, and you will likely not see the great collision of the Milky Way and Andromeda in 4.5 billion years. You will not know how future civilizations will witness that lonely age when the sky becomes completely dark. On the cosmic timeline, you are less than a whisper. To leave a permanent mark seems almost impossible at this scale. Because the universe seems poised to flow on, oblivious to your existence. But here comes that but again. Because you're not just a part of that infinite time, you're a witness to its most important moment. You may be living in the most interesting, most meaningful period of the universe. We exist in that brief, incredibly lucky sliver of time, just before the universe erases its own history. We opened our eyes and our telescopes in an age when the cosmic microwave background is still visible, when the light from the most distant galaxies can still reach us. Whether this is a coincidence or has a deeper meaning, we cannot know. But the truth is, you are living in one of the rare moments when the universe can read its entire story. Your short life is a window into the 13.8 billion-year memory of the cosmos, and you, by looking through that window, are gaining knowledge that can shape not just the past, but the future. And so, the transience of time is not a curse, it is a gift. Because it reminds you how precious every moment is, and that the knowledge you have now is a treasure that may never be known in the future. The third and perhaps deepest paradox is between loneliness and connection. On one hand, you have the unimaginable silence of the cosmic void, isolated islands of galaxies, drifting in the dark, millions of light years apart, star systems closed in on themselves, and that overwhelming, cold nothingness in between. But, on the other hand, there is you, again and again, and there is us. Every single carbon atom in your DNA was forged in the heart of a star billions of years ago. Every oxygen molecule you breathe was scattered into space by a supernova explosion. The fundamental materials that make you came from all over this universe, at different times, from different stars. You are, quite literally, stardust. So, how can we be so deeply interconnected in such an isolated universe? The tragic truth is, we often do not feel this connection. In the hustle and bustle of daily life, it is hard to think about the sacrifice of a supernova billions of years ago, or to grasp the fact that the iron in our blood came to us through the death of a distant star. We feel like isolated individuals, trapped on this small planet, in our own small lives, and when we look up at the sky, that dark void can deepen this sense of loneliness. Because we cannot touch any of the stars out there, we cannot make our voice heard by any galaxy, the silence of the universe can be deafening. But, here comes that magical but once more. Because you not only feel that connection, you prove it. Science is the most concrete expression of this connection. The James Webb Telescope is not just a machine, it is a symbol of thousands of people from different countries, different cultures, different languages, coming together for a common purpose. Every single data packet that comes from that telescope is a product of humanity's collective curiosity, collective effort. When you learn about the findings of that telescope, you are not just acquiring information. You're also forming an invisible bond with an engineer who worked on that project, a scientist who analysed that data, and millions of other people who share the excitement of that discovery. We may be lonely on a cosmic scale, but on a planetary scale, we are more connected than ever before, and this connection is the most powerful tool we have to solve the greatest mysteries of the universe. Because you are part of this universal human project, and that is a connection that will never leave you alone. But beyond these connections, there is another truth, perhaps the most uncomfortable one. Because, despite all this beauty and meaning, we must face the fact that the universe is indifferent to us. And how does that indifference shape our ultimate destiny? Because the real question is not what the universe is telling us, but whether we are listening. We are. And so, everything we have uncovered so far leads us to the next, perhaps most uncomfortable paradox: knowledge and ignorance. On one hand, we are living in the most knowledgeable age in human history. Thanks to instruments like James Webb, we know more about the universe than our ancestors could have ever dreamed. We can calculate the age of the universe to be 13.8 billion years. We can read the chemical makeup of the most distant galaxies. And we can even map the oldest light left over from the Big Bang itself. This is an unprecedented age of enlightenment. But, on the other hand, every new discovery by Webb slaps us in the face with how little we actually know. Every answer gives birth to 10 new questions. Every solved mystery reveals a deeper, more complex unknown. So, how can we be both so knowledgeable and so ignorant at the same time? The tragic truth is that we're beginning to realize how fragile the foundations of everything we thought we knew are. We have seen our standard model of cosmology completely collapse in the first 1% of the universe. We have discovered that a fundamental principle that should hold the universe together is being violated by 10 billion light-year-wide structures. And we have faced the fact that our own measurements may be distorted by a massive void we live in. Our knowledge is like a sand castle. As the waves approach, it seems ready to collapse at any moment. Because the more we learn, the better we understand how deep the ocean of our ignorance is. This can create an intellectual vertigo, a doubt about whether the human mind can truly grasp these ultimate questions. But here comes that but again, throwing us a life raft. Because this ignorance is not a weakness, it is our greatest source of motivation. If we knew everything, what would be left to discover? If all questions had answers, what reason would we have to wake up in the morning? The existence of the unknown is the engine that pushes us forward. It is the spark that ignites our curiosity, and it is the force that makes humanity's greatest achievements possible. you are a part of this great quest. Every article you read, every documentary you watch, every question you ask takes you one step further into that ocean of ignorance. And you're not just a consumer searching for answers, you're also a participant helping to find those answers. Because science is not the work of a few geniuses in a lab. It is a collective effort, fueled by the support, interest, and passion of curious people like you. And so, we should not fear our ignorance. We should embrace it. Redshift, because it reminds us not how far we have come, but how much further we can go. This brings us to a final contrast: chaos and order. On one hand, there is the violent, chaotic nature of the universe, the destructive explosions of supernovae, the insatiable appetite of black holes, the galaxy-shredding collisions. We have seen that the early universe was an age of hyper-efficient violence that flouted the rules, and we have understood that the future may bring either a freezing death or a catastrophic rip. The universe seems to be a fundamentally dangerous and unpredictable place. But, on the other hand, there is the incredible order that emerges from that chaos, the elegance of the laws of physics, the precision of mathematics, and most importantly, the emergence of life itself. How can such violent chaos give birth to such delicate order? The tragic truth is how exceptional and how rare that order is. The conditions necessary for life are as thin as a knife's edge. If our planet's orbit were just a few centimeters different, we would either freeze or roast. If the ratio of gases in our atmosphere changed slightly, we would suffocate. The vast majority of the universe is lethally hostile to life. Cold, empty, full of radiation. Our existence is like winning a cosmic lottery, but a single winning ticket after billions of blank ones. This can create a sense that our existence may be meaningless and coincidental. Because we may not even be a footnote in the grand cosmic plan. But here comes that final but, perhaps the most powerful one. Because being rare does not mean being meaningless, quite the opposite. What is rare is more valuable. We are the island of order in this ocean of chaos. We are the point at which the universe gains consciousness, becomes self-aware. The violence and chaos do not make our existence meaningless. On the contrary, they make our existence a miracle. You are the living proof of this miracle. Your existence is the result of billions of years of cosmic evolution, countless star explosions, and a delicate physical balance. You are the most complex, most beautiful order to emerge from chaos, and your task is to understand, to protect, and perhaps to spread this order to other parts of the universe. Because you're not just a product of the universe, you're also a part of its future, and so, finding order in the midst of chaos is not a hopeless endeavor. It is the most fundamental purpose of our existence. When we consider all these paradoxes, we oscillate between greatness and smallness, infinity and transience, loneliness and connection, knowledge and ignorance, chaos and order. We now know that we are both the most insignificant and the most important part of this universe. We are both a momentary flicker and a window into eternity. We are both hopelessly lonely and deeply connected to everything. But, beyond all these philosophical reflections, there is a more practical, more urgent question. Faced with this actively self-erasing nature of the universe, what should we do? If the cosmic horizon is closing and information is being lost forever, what kind of responsibility does this place on our shoulders? Because this is not just a thought experiment. It may be the greatest challenge our species has ever faced. And this challenge is preparing us for our ultimate destiny and the final act of the universe. It prepares us. And so, we must now confront a deeper, more internal question. We've understood that the order within chaos is a miracle, and that we are part of this miracle. But this knowledge places a heavy responsibility on our shoulders. The fact that the universe is indifferent to us leads us to an ultimate paradox, perhaps the most human one of all: meaning and meaninglessness. On one hand, there is the most fundamental drive of human nature, the search for meaning. We tell stories, we make art, we engage in science, we produce philosophy. Because we want to attribute a purpose, a reason, a lasting value to our existence. But, on the other hand, there is the universe itself, a vast, indifferent machine operating according to physical laws, with no purpose, no reason, no value. How can these two truths coexist? How can the meaning we so desperately seek be reconciled with the meaning the universe so blatantly lacks? The tragic truth is that in the grand scheme of the universe, your personal life, your hopes, your fears, your loves, and your losses may have no meaning. Billions of years from now, when you, me, and everything we know is gone, the universe will not even notice. Because it is a mechanism without emotions. Your existence is neither a gain nor a loss to it. It is just a temporary arrangement of atoms. This can create a deep existential dread. We can feel that everything we do, everything we feel, is ultimately empty and meaningless, because our efforts are like a grain of sand thrown into the cosmic ocean, and the waves will inevitably swallow it. This is the cold embrace of nihilism. But here comes that magical but, appearing one last time to pull us back from this abyss. Because, boss, the universe may not have a meaning. But that doesn't mean you cannot create meaning. Meaning is not something to be discovered in the universe. Meaning is something you bring to the universe. You are a meaning-making machine in this indifferent cosmos. The value you give to the people you love, the work you do with passion, the compassion you show to others, everything you learn and teach, is a layer of meaning added to this universe by you. The universe may not give you a purpose, but you can create your own purpose, and this elevates you from being a passive victim of the universe to its active partner. The meaning you create may not last for billions of years, but that's not what matters. What matters is that it exists now, here, for you and for those around you. Because you're a miracle that creates meaning in a meaningless universe, and that can make you even more powerful than the universe itself. This brings us to another profound dilemma, the tension between action and acceptance. On one hand, we have the knowledge of the universe's inevitable end. Whether it's the big freeze, the big rip, or the big crunch, we know it all has an end. This knowledge can push us toward a kind of passivity, an acceptance. If everything is going to be destroyed anyway, why do anything? Why try to create a better world? Why strive to improve ourselves or our species? Isn't it all in vain? This is a form of fatalism. The tragic truth is that this argument has a certain logic. Yes, on a cosmic scale, the ultimate result of our efforts may be zero. No empire lasts forever, no monument is permanent, and no species can outlive the universe itself. This can create a deep melancholy about the futility of our actions. Because we are players in a game with a known end, and the curtain will inevitably fall. But here comes that transformative but again. Because knowing the end of the game doesn't mean we should stop playing. Quite the opposite. Knowing the game is limited makes it more precious. Does knowing the end of a movie reduce the pleasure of watching it? Or does it make us listen more carefully to every moment, every dialogue? Your life is like a short film in the grand cinema of the universe, and you are both the director and the lead actor. Knowing the end is coming should not paralyze you. It should encourage you to make the most of the time you have. How much love, how much knowledge, how much beauty can you create in this short film? That is the real question. Action is our greatest rebellion against meaninglessness. What we must accept is the inevitability of the end. But what we must not accept is walking passively to that end. Because you're a being who chooses to dance, even knowing the end, and that dance itself is the ultimate victory. Finally, we face the paradox of loneliness and legacy. On one hand, there is the cosmic loneliness of our species. So far, we have found no other intelligent life in this vast universe. The Fermi paradox haunts our minds with the question, where is everybody? Perhaps we are truly alone, a single conscious species in this vast, silent universe. This can be a terrifying thought. The tragic truth is that this loneliness places an incredible weight on our shoulders. If we are the only conscious species in the universe, then the extinguishing of the flame of consciousness is not just our end, but the end of the universe's ability to know itself. This represents a loss that will never be repeated. This responsibility can be overwhelming, Because we live not just for ourselves, but perhaps for the entire universe. But here comes that final but, the most hopeful one. Because being alone does not mean we cannot leave a legacy. Quite the opposite. Being alone means the legacy we leave is even more important. Our legacy is our children, our books, our works of art, our scientific discoveries. These are the proofs that we existed in this universe, and perhaps, billions of years from now, another intelligent species will find our ruins, our Voyager record, our radio signals. And in that moment, we are no longer alone. We become part of a dialogue that transcends time. You are a part of this legacy. Every day you live, every word you speak, every kindness you perform is a signal you send into the future. Your task is to ensure that this signal is as strong or as clear and as full of love as possible. Because you're writing a letter to our unknown friends in the future, and what is written in that letter is entirely up to you. Our loneliness is not a curse, it is our greatest mission. A mission that reminds us how precious the legacy we leave behind is. Meaning and meaninglessness, action and acceptance, loneliness and legacy. These paradoxes define what it means to be human, and what the Webb telescope has shown us is that these paradoxes are not just philosophical exercises, they are truths woven into the fabric of the universe. But these thoughts bring us to an ultimate gate. What does our knowledge of the universe's end tell us about our own end? And more importantly, when faced with this knowledge, what kind of species will we decide to be? Because the ultimate test is not acquiring knowledge, but what we do with that knowledge. And so, this ultimate test brings us to the final philosophical layer of our cosmic journey, the three possible doomsday scenarios the universe presents us with. To understand what we will do with this knowledge of the final act that science has given us, we find ourselves in another fundamental paradox, knowledge and fate. On one hand, through science, we have gained an incredible ability to foresee the future. Our models tell us that the end of the universe could be the slow, cold silence of the Big Freeze, the violent atomic shredding of the Big Rip, or the fiery singularity of the Big Crunch. This is knowledge that no generation in history has possessed. But, on the other hand, this knowledge itself comes with the fact that we cannot change this destiny. We know our fate, but we cannot control it. So, what does it mean to know a fate you cannot control? The tragic truth is that this knowledge can make us feel helpless, like knowing a train is coming towards us, but being unable to get off the tracks. This knowledge can seem like a curse, not a blessing. Because it constantly reminds us of our own powerlessness and the overwhelming power of the universe. Knowing that future generations, no matter the scenario, will face an inevitable extinction can make our current efforts seem meaningless. This can create a deep despair. Because, if the end is inevitable, why fight? This is a feeling of existential fatigue. But here comes that magical but. One more time, lighting a candle in the middle of these dark thoughts. Because, even if we cannot change our destiny, we can choose how we walk towards that destiny, and that choice changes everything. Yes, we know what the end will be. But the path to that end has not yet been written. That path will be shaped by our actions, our decisions, our values. We are the authors of a story with a known ending, and knowing the end of the story gives us the opportunity to write that story in a more meaningful, more beautiful, and more courageous way. You, as an author of this story, can decide how to write your chapter. Will you fill your chapter with fear or with hope, with indifference or with love? This choice is in your hands, and this choice is a freedom that not even the universe itself can take from you. Because you can choose to live honorably despite your fate, and that choice itself is a victory over fate. This brings us to the next dilemma, the delicate balance between memory and oblivion. On one hand, there is the fact that the universe will inevitably erase everything. When the cosmic horizon closes, billions of years from now, no trace of our existence will remain. Not our books, not our cities, not our memories. Everything will be forgotten in the expanding void of time and space. This is the ultimate tragedy of existence. Because we are beings who live to remember. But The universe is a machine programmed to forget. The tragic truth is that all our achievements, all our sacrifices, and all our love will eventually dissolve into a cosmic nothingness. This creates a feeling that everything we do is temporary and fragile. Because odd, we are a species writing on water, and the waves will inevitably erase that writing. But here comes that but again, offering us a different perspective. Because Gahal, the universe may forget, but we do not forget, and as long as we remember, nothing is truly lost. The legacy of a person is not the buildings or books they leave behind, but the mark they leave on the hearts and minds of others. And this mark can be passed down through generations. You are a legacy of your ancestors. Their stories, their genes, their wisdom live on inside you. And you too will leave a legacy to your own children, your own society, your own time. This is our greatest resistance against the ruthlessness of time and oblivion. The universe may erase everything on a grand scale. But we, on a small, human scale, can keep each other's memory alive. You're a part of this living memory, and your task is not just to live your own story, but also to honor the story of those who came before you, and to pass it on to those who come after you. Because we are a species that lives forever in each other's memories, and that is an immortality that not even the universe can erase. Finally, at the end of this journey, we are left with the final confrontation between fear and curiosity. On one hand, there is a deep, existential fear created by everything we have learned in this documentary. The vastness, the indifference, the violence, and the inevitable end of the universe. Facing these truths can make a person feel small, powerless, and scared. The tragic truth is that this fear is completely logical and understandable. We fear the dark, we fear the unknown, and we fear forces we cannot control. The universe is the ultimate combination of all these fears, and this fear can paralyze us. It can push us to run away from these truths, to ignore them, or to console ourselves with simple answers. But I say, here comes that final, brightest but. Because just as one of the most incredible features of the human spirit is that where there is fear, there is always curiosity. Yes, we fear the dark, but we're also madly curious about what is in that darkness. This curiosity is the force that brought us out of our caves, enabled us to cross oceans, and ultimately took us to the stars. The James Webb Space Telescope is a monument not to fear, but to curiosity. It is a victory of humanity saying, "I don't know, let's find out," instead of saying, "I don't know and that scares me." You are an inheritor of this victory. By choosing to watch this documentary, you have surrendered not to fear, but to curiosity. Instead of retreating in the face of the unknown, you have taken a step towards it. And this is the most fundamental definition of what it means to be human. Fear allows us to survive. But curiosity allows us to live a life worth living. Because you are a miracle that chooses to ask questions, despite your fears. We now know that we are both the most insignificant and the most important part of this universe. We are both a momentary flicker and a window into eternity. We both know our fate and have the freedom to choose how we walk towards that fate. Our memories will be erased, but we will live on in each other's memory. And yes, the universe is frightening. But our curiosity is greater than any fear. As we come to the end of this long and deep journey, in the light of all these discoveries, all these paradoxes, and all these philosophical reflections, we find ourselves back at the starting point. But we are no longer the same people, because we have seen the true scale of the universe, and this has forever changed not just our view of the universe, but our view of ourselves. Now, in the light of all this knowledge, it is time to face one final question. Who are we, and what is our ultimate place in this universe? We have seen the immense scale and shocking truths of the universe. But there is something I haven't told you. What if this 93 billion light-year universe isn't real? What if all these galaxies, stars, and even you are a hologram, projected from a distant two-dimensional surface? In our next journey, we will question whether reality is an illusion. Are you ready to enter the holographic universe? Humanity built a $10 billion golden eye to see the limits of the universe, the James Webb Space Telescope. Its purpose was to place the final piece of the map. But Instead of completing the map, it proved that everything we knew was wrong. The depths of the cosmos were not empty as we expected. We saw how a 13.8 billion-year-old universe expanded to 93 billion light-years. And in this vast space, we discovered structures that were physically impossible to exist. Galaxy walls a full 10 billion light-years long. But what's truly unsettling is what the existence of these structures means. If you're curious about the truth behind this cosmic deception, you're on the right channel. Subscribe now, because the true scale of the universe is far more terrifying than we thought. We're beginning.